Welcome to the Explainer. Look, today we're cutting straight through the hype of cryptocurrency. We're translating all that noise into pure engineering language. We're talking distributed systems, databases, and network latency. If you're a software engineer, you already know how to reason about consistency, fault tolerance, and trust boundaries. Today, we're going to apply those exact same principles to figure out what crypto actually is under the hood. All right, let's dive right in with a question that completely flips traditional system architecture on its head. Think about this for a second. What if no central server held the ultimate truth? You see, a traditional bank is, at its core, really just a database with strong access controls and a regulatory wrapper. Crypto is what happens when you ask what it takes for the network itself to enforce the rules, without deferring to any single authoritative database. So here's our tech stack for today. We're going to cover 1. Money as a system. 2. Math replaces the server. 3. The replicated state machine. 4. Immutable serverless functions. 5. Engineering the exchange. And finally, 6. Custody and paranoid security. Kicking things off with Section 1, Money as a System. When you really think about it, money is just tech with a spec sheet. Whether you're talking about gold, US dollars, or Bitcoin, good money needs durability, portability, divisibility, fungibility, scarcity, and acceptability. But here's the catch. You always have to make trade-offs. No money is perfect on all 6. The honest reading here? Bitcoin trades widespread acceptability for provable scarcity and, honestly, absolutely incredible global portability. But creating digital money isn't just about ticking those boxes. For 40 years, digital cash was totally blocked by one massive computer science hurdle. We call it the double spend problem. Because in a purely digital system, data is trivially copyable. Like if I email you a file, I still have my copy, right? So the big challenge was, how on earth do you enforce a uniqueness constraint on data so someone can't just copy and paste their digital money and spend it twice? Now, look at this stark architectural contrast in how we actually solve that problem. Traditional finance? It enforces this uniqueness constraint using a centralized master database. You essentially trust one entity, a bank, to keep the canonical ledger. But crypto chose a totally different path: decentralized trust. It relies on a leaderless network of thousands of peer nodes that use a shared consensus protocol to agree on the state of the ledger, completely avoiding the need for any single owner to control the truth. Moving right along to Section 2, Math replaces the server. Okay, so in a blockchain, there are literally no usernames, no passwords, and absolutely no central database verifying who owns what. Instead, blockchains use a public-private key pair. It's a total paradigm shift. Your public key acts as your identity. It's just an address you can share with anyone. Your private key, though, that gives you absolute control over the funds. And digital signatures are how you prove your authenticity to the network. You show you authorized a transaction without ever revealing the secret private key itself. To secure all this data, the network leans heavily on cryptographic hash functions, like SHA-256. Honestly, think of them like a one-way meat grinder for data. You can put a whole cow in and get a hamburger out, but there is absolutely no way you're reconstructing the cow from the burger. More importantly, they utilize what's called the avalanche effect. Changing even a single bit of input completely scrambles the output. This makes any data tampering instantly, undeniably visible across the entire network. That brings us to Section 3, the replicated state machine. So how does a transaction actually move through this system? Well, it starts as a signed intent in your wallet. It's then broadcast out to the network's mempool, which is basically a giant waiting area for unconfirmed transactions. From there, a miner or a validator pulls it into a block, and finally, as more blocks get stacked on top of it, it reaches cryptographic finality, becoming a permanent, irreversible part of the ledger. Now, as an engineer, you are definitely going to spot the trade-offs here. A traditional system is just a database behind an API with a trusted operator, which allows for massive throughput. A blockchain, it removes that trusted operator entirely, relying on cryptography and consensus rules with total replication across thousands of nodes. This trade-off is brutal, guys, but it's totally intentional. Blockchains sacrifice massive amounts of throughput and performance to buy trustlessness, extreme redundancy, and censorship resistance. Let's jump into Section 4, immutable serverless functions. I absolutely love this definition from our sources because it perfectly translates smart contracts into a language we actually understand. They aren't legal contracts, and honestly, they aren't even smart. A smart contract is a stored procedure that lives on a public, append-only database where every invocation is a paid, signed, replicated remote procedure call. Seriously, they are essentially immutable serverless functions, kind of like AWS Lambdas, except they run on a global database. But heads up, building on this layer is going to completely invert your normal engineering instincts. First off, these contracts are deterministic, meaning absolutely no random numbers or external API calls. Their bytecode is public and world readable. They're permissionless, so literally anyone can call your public functions. And crucially, they are immutable. This means a deployed bug is permanent. Well, unless you explicitly engineered an upgrade path in advance using something like a proxy pattern. It's wild. Okay, on to Section 5, Engineering the Exchange. So, if you're building an exchange, your Web 2 instincts might be screaming at you to horizontally scale your microservices to handle high trading volume, right? Well, actually, an exchange's matching engine has to be a single-threaded, in-memory, deterministic sequencer. It absolutely has to process orders strictly by price-time priority. You cannot have race conditions when matching a buyer and a seller. So one market runs on one thread, processing one order at a time. You scale by sharding markets, definitely not by parallelizing a single order book. And this right here reveals the dirty little secret of centralized exchanges. They are essentially just an internal off-chain ledger, basically an IOU casino. When users trade, it's really just fast internal bookkeeping updating database balances. The trades are instant and completely free of gas fees because the actual blockchain is only ever touched for net settlement, like when users physically deposit or withdraw their crypto from the platform. Finally, let's look at Section 6, Custody and Paranoid Security. Because a centralized exchange holds the keys to all those user deposits, it becomes a massive honeypot for hackers and even nation-state attackers. To defend it, we have to rely on incredibly specialized infrastructure, things like hardware security modules, HSMs, and multi-party computation. This ensures that private keys are never ever exposed in plain text to an application, and no single employee can ever move funds unilaterally. You have to be deeply paranoid. But wait, how did these keys even get created in the first place? It actually happens through a highly scripted key generation ceremony. We're talking clean rooms with air-gapped hardware that has literally never touched the internet. It uses verified entropy to ensure true randomness. Then, that resulting secret is mathematically split into shards using Shamir's secret sharing. These shards are distributed to different officers, enforcing strict segregation of duties, so no one single person knows the whole key. And beyond the math and cryptography, you have to enforce strict operational discipline. This means least privilege with no standing access. Engineers only get just-in-time access for specific tasks. It requires strict separation of duties, hardware MFA everywhere like YubiKeys, and immutable audit logs. In crypto, the risk hasn't disappeared, it's just shifted. You've gone from trusting a traditional banking institution to trusting your own strict internal controls and code. It's all on you. I want to leave you with a final, provocative thought to conclude our explainer today. At the end of the day, crypto sacrifices high throughput and reversibility in order to achieve trustlessness and sovereignty. It is a fascinating, radical engineering trade-off. So before you start building your next project on a blockchain, you really must ask yourself, is your specific problem truly worth paying that price? Thanks for joining me for this explainer, and keep building out there.